Log on, tune in, find out. Another good idea from Cambridge.
Iskander Kalimullin from Kazan, and he will speak about Limitwise, monotonicity, spectra, and uniformity.
I want to say thanks to organizer for giving me a possibility to work here during this program. So I will start. I want to introduce the topics in which I am interested and working during the planning to study being here. Okay. First, my topic can be introduced via some computable notions on abelian group, some specific abelian groups. And in general, this is notion can be considered not only for groups. It's a common definition for algebraic structure in general, but I consider only countable abelian group. A countable abelian group G is X-computable if it has an isomorphic copy on which is computable on the natural numbers. So the group operation, if a group operation can be computable and n with this operation is isomorphic to G, then G is X-computable. If the operation is X-computable, then the group is X-computable. And the spectrum of G consists of all reals X such that G is X-computable. Usually it's called degree spectrum, but degree spectrum it's in the case when we consider the Turing degrees of these reals. Here it's more convenient to consider just reals. And we will say that one group is more hard than another group, G2. If the first degree spectrum is a subset of the second degree spectrum. This means that if we can compute a copy of G1, of arbitrary copy of G1, then we necessarily can compute a copy of G2. But this is not uniform version. The more uniform version of this definition, if it's in the case when we can compute a copy of G2 using some fixed procedure on those inputs, we'll put arbitrary copy of G1. In this case, we say that G1 is uniformly more hard than G2. Well, it's these notions, last two notions, are technical. It's not common, but during the talk, my talk, it's more convenient to use this notation. And now I describe general problems for computable model theory, in which I am interested, of course, but it looks like it's some difficult, big problems. It's not known which spectra of abelian groups can be possible. It's not known precisely when one abelian group is more hard than another abelian group. And if it is the same is these two notions more hard and uniform hard? Are these notions the same? It's also not known. And in general, it's not known is these relations for on groups is arithmetic, hyperarithmetic, or what is the difficult? What is the difficulty of this group? Or this relation on the countable groups? Formally, it is. It's not hyperarithmetic. It consists the quantifiers of the isomorphisms. So Yes, it's spiral. But maybe if these two notions are the same, then it may be more easily to describe this notion. And in fact, we will see that these two problems. I want to also say why I consider only abelian groups, not just other groups. In fact, for general groups, these problems, in fact, it's known that the situation is clear for them, in the sense that the situation is definitely unclear, because any group can be, any structure can be encoded into some non-abelian group. And in this case, this means that it's arbitrary group can be constructed very difficultly at the spectrum, and other computable notions can be very difficult, and it's difficult to describe even computable groups. It's no hope to solve such question. For abelian groups, there is some small hope that it could be solved in some. But in fact, this problem is difficult even for some special abelian groups, which we will now consider. In fact, during the talk, I will I will say only about this specific P group. If P is prime, then we can consider, and A some real, some subset of naturals. When GA, it will be fixed notation during the talk. It's direct sum of cyclic groups of the length P to N, where N belongs to A. So it's some direct sum of cyclic group, cyclic P groups. There is a description. It's old result of Samif when such groups are computable on the language of so-called S1 functions. I will not give the exact Samif definition of S1 functions. I will give alternative definition, which looks like similar and equivalent, in fact. It's in fact such group is computable if and only if A is a range of a limitwise monotonic function. A limitwise monotonic function means that A is a range is such function f, which is a computable limit of it is a limit of computable functions g, which is not decreasing with respect to the second argument. And in fact, this characterization, in fact, can be is relativizable. So we can put arbitrary oracle, arbitrary real as oracle. It's again will be the same. So this means that the spectrum of this group is exactly all reals x, such that A is a range of x element. Of an x limitwise monotonic function. In trivial case, we will say that A is in trivial case if A contains an infinite limitwise monotonic subset. For example, it can be set A B plus omega. It means that all odd numbers are subset in this case. The set of all odd numbers is a subset of A. In this case, the spectrum can be described very easily. It's a collection of all reals x, such that A is C in the Turing jump of x. This means that, in particular, that is the measure of this. We can on the set of reals we can consider the usual measure. uniform measure on the Cantor space. If the measure is non-zero of this collection, then in fact the spectrum, it's some misprint. Oh, sorry. This is misprint is again spectrum. Then the spectrum contains all degrees. It's and the same we will have if the spectrum contains some low set. If it contains some low set, then this means that x prime is equal to 0 prime. So if it contains, so it means that the spectrum contains 0, and if it contains 0, then it contains all degrees. This is trivial case. And in fact, it's not interesting. It's such spectrum can be described very easily. It's not common case even for our direct sum of cyclic groups. But also in this trivial case, we will see that uniform version we will have uniformity. In fact, if A and B are in trivial case, then GA is more hard than GB. It's exactly when B is irreducible to A plus zero jump, the enumeration zero jump. It can be described via enumeration reducibility. And this means that, of course, this is arithmetical. Relation, and moreover, we in this case can uniformly construct a copy of GA given an arbitrary copy of GB. It is known that there are non-trivial cases which are more interesting. The first one, I guess, was constructed by Wallbaum in his PhD thesis. In fact, there is a delta 02 set such that the spectrum of GA has measure 1, but 0 does not belong. That means that for almost all, this group is computable in almost all reals, but it cannot be computed without oracles. So it's a strange situation, but such a situation is possible. It was known that it's possible in computable model theory. And also, because my talk is about uniformity, I want to note that for these examples, for any such examples, no uniform procedure which allows to construct a copy of GA. Given the measure 1 is not uniform measure 1. That means that no one procedure which is this can be considered as random machine which will construct a copy of GA given random data and it cannot produce the copy of GA with probability 1. It's always, it will be some probably non-zero probability, but less than 1. Another two examples. Another example. It's known that there is a sigma 02 set such that the spectrum contains all non-zero delta 02 degrees, but it does not contain 0. So in particular, it contains any low degree, but it does not contain 0. Another example, the last example, which is in fact no of non-trivial case. There is a delta 02 set such that the spectrum has measure 1, measure 0. So it's surely it is it cannot be a trivial case, because if A is delta 02, then it must be CE in all jumps. So it should contain, in this case, it should contain all degrees, not and the measure cannot be 0. So, and in fact, it's all known examples of non-trivial cases for a spectrum of abelian groups of this specific group. And I want to note that it's in these examples, it's not known that there are some there is some complete description of at least one set A of in non-trivial case. The complete description of the spectrum of this set, of this abelian group. And in fact, the Limitwise monotonic property is connected with enumerability of families very tightly. We will say that a countable family F is X-computably enumerable if it can be uniformly enumerated using some computable function F using the oracle X by the following way. And we know that it's very easy to note that A is a range of X Limitwise monotonic functions. So that means that X computes a copy of our abelian group. If and only if the family of initial segments of the natural numbers of the length n belonging to A restriction n, it's exactly this initial segment, is computably enumerable. So if we, for a fixed set A, consider a family of initial segments, then this family will be X-computably enumerable exactly when A is a range of X Limitwise monotonic functions. So this means that the spectrum of our group GA, it's exactly all reals, such that the family LMA is uniformly XC, is XC. And again, for families, we also can give the definitions for one family being more hard than another. So this again means that if we can use one oracle to enumerate F1, then we can enumerate F2. And uniformly more hard, that means it's just it's uniformization of the first definition. And the open problem in which I am interested, in fact, it's which is connected with the previously declared questions. Though there are two sets, A and B, such that LMA is harder than LMB, but not uniformly hard. And in more general, I am interested is these relations on sets is arithmetical. Can we do some nice description of this relation? But maybe if we answer to this question, then it can be become clear. But still, it is open problem. But it is on. In fact, it's for computable model theory, for computabilities in general. It's not very common when we have non-uniformity of in this sense. Usually, when some family is more hard than another, usually we can do some uniform procedure. But in fact, it is known that it's not always. There are some artificial families of finite sets, such that F1 is harder than F2, but not uniformly hard. And for this, we need so-called Werner's family. It's artificial family. It consists of the joints of singletons n and finite set F, such that F not equal to the nth C set W. And it is known that f1 is xc if and only if x is not computable. So in this case, we know when we can enumerate. And this implication is uniform. In fact, there is one procedure which allowing to enumerate f1 using arbitrary non-computable oracle x. But the second, for the second family, for the second part, this family is more natural. We need to fix some uniformly low sequence of non-computable sets which are formed pairwisely or form minimal pairs in Turing degree. It's easy to construct such sequence. But in this case, it should be f2 here. In fact, it should be f2, not f1. And in fact, if this family is not, it cannot be uniformly in comparison of the previous family. This family cannot be enumerated using arbitrary computable oracle by a fixed procedure. If there is a computable function f such that f2 equals to the collection of all wx fn for all n, then in fact we can substitute x instead xm instead x, and then we will have wxm fm not equal to wxm m, because this is a member of a family, and and in this case we will have a contradiction with recursion theory. And this means that f1 is not uniformly harder than f2. But for this family, we will still have non-uniformly. We will have that the spectrum for this family is the same as the first family. In fact, f2 is xc if and only if x is computable. But the proof now must be non-uniform. How it works? It works. In fact, to enumerate f2, this family, is enough to have a set y, some fixed set y, which is not almost equal to wxn n for all n. So we need to have some set y which is different from other from this set wxn wn with oracle xn. I'm using a star here. This means that it should be different from each set on infinitely many elements. Equals with star means that the sets may be not equal, but the symmetric difference is finite. Here, the symmetric difference between two parts must be infinite. If you have such set, in fact, it's not difficult to show that it's enough. For this, we need that the sequence xn is uniformly low, and this allows to control this set, this expression. If xn is uniformly low, wnxn is some uniformly delta 02 set, and we can, and using this we can enumerate if we have this set y, which is different from all others. But in this case, non-uniformly, we can find this set y for in every non-computable oracle x. In fact, if x is not computable, then we can take either y equals to this set x plus x bar or x bar plus x is two different sets which are not equal to each other, but sets theoretically. They are in fact disjoint with each other. And if, by this reason, if both sets fails to have this property, then we will have that x plus x bar almost equal to w xn, and x bar plus x almost equal to, I forgot to let's start here. X bar plus x also must be almost equal to w xmm. And because these two sets are disjoint, n and m should be different. N and m cannot be the same in this. But this means in the same time, this means both expressions guarantee that x is Turing computable in xn, and because here it's two parts x and the complement x. If if both sets are completely enumerable in xn, then x is computable in xn, and the same for xm. X should be computable in xm. But we have chose the sequence xn as minimal pairs in Turing. So this is impossible if you take x is not computable. By this reason, one of these two sets satisfy our property, but of course it's we do not know which of sets we need to choose. But one of these is enough. When we choose this set y, we can enumerate this family. But unfortunately, this proof cannot be adapted to, cannot be easily adapted to our case for abelian groups or GA. And the main difficulty here is that we do not know examples, interesting examples of spectrum which is fully described in non-trivial cases. It's only these examples are known. In other examples, we cannot construct some set which is surely non-trivial, but for which we can easily describe in which sets GA will be computable. We cannot fully describe the spectrum. And so, and by this, the second connected problem in which I am interested is that I set A with fully describable spectrum GA in non-trivial case. So the spectrum cannot be in this form. Thank you for attention.
Questions? In this uniformity, you wanted to say if you're given an algorithm for computing a presentation.
No, this means that it's an algorithm with oracle.
Yeah. Well, yeah, relative to the oracle, then you can uniformly produce an algorithm.
Yeah.
But I guess you can weaken it that you have like 5 different possible algorithms for the second structure, one of which works, but you don't know effectively.
Here, the previous, in this example, it's exactly 2 algorithms.
So I guess you could generalize this and make sure that.
Maybe. It's in fact, it's it was sufficiently difficult to find this example. It's.
Right.
I do not know
it's
how
almost
to
uniform, right? You have 3 possibilities, one of which works. You just don't know which.
There is no technology how to produce such examples. It was found almost randomly, maybe. I do not present in general a nature when such non-uniformity appears, and when it appears, why it appears.
Comment? Yeah.
Are there other classes of groups GA? for which you could develop the same kind of process?
No, we can some it can be some like generalized with groups. For example, you can do the same, for example, for a sequence of sets. If some sequence of sets is fixed, is it A0, A1, A2, A3, and so we can consider the direct sum of these groups, but for each set we take a different prime. So you fix, for example, the natural ordering of primes P1, P2, P3, and take the direct sum.
But this particular,
And almost anything works here.
but again, it would be some typical sort of direct sum of appropriate
Yeah.
groups.
But in general, for abelian groups, it's there are another codings, but they use another computability stuff. There are some. In fact, I began to interested in abelian groups after working with Sasha Melnikov. It's a young mathematician. He's best specialist in abelian groups, and he knows many codings in for example, it can be not. This is p groups, and there are codings to divisible groups. It's a lot of stuff, but each coding requires different notions in computability theory and another consideration. I guess this is for computability theory. This is more natural. This is most easy coding.
Other questions? All right, thank you again, Iskander.